Welcome to an introductory video for the PHAS0030 Computational Physics course, the 9th session on integral transforms and representation of functions. We're doing this online today because of the ongoing global health issues over the COVID-19 virus. Just before we start, a couple of bits of administration. First of all, I'd like to remind you please to complete the course evaluation, which is available on Moodle. You can see where the tab is on the picture below. This is really helpful to us to know how the course is going. You can make suggestions for ways that we can change it. You can give feedback on specific parts of the course. And we always take into account the comments that people make on these. And so I would ask you to do that as soon as you possibly can. A little bit of administration just before we carry on with the actual information for today. Please keep working on the mini projects. The deadline is still this Friday, March the 20th at 6 p.m. Unless you have a Sora. Just to remind you, you should not be using data structures or modules beyond what has been taught in the course unless you've discussed it with your supervisor and me and had that approved. Your reports should actually be in reasonably good state by now. You should have got the basic data and results for the report. Your logbooks should also be ongoing. You remember you should be recording what you're doing in your logbook as you do it, and in particular you should be recording any discussions that you have with your supervisors. When we mark it, we will be considering mainly your computational physics and your approach to science rather than your coding skill. A reminder that there is an assessment for today's session, though it won't be marked, and there's a data file available for you to work on just to make that a little bit simpler. The exam will still be on Monday, the 23rd of March, that's a week today. It's not yet clear exactly what the arrangements will be. It will be online in some way. I will post on Moodle and I will send out an email nearer the time when we have the full details. So today we're going to be talking about representing functions and about integral transforms. We'll start by giving a general introduction to the idea of representing functions. We'll then move on to Fourier transforms, give you the basic outline of what we do, and then we'll talk about some more detailed and more advanced parts of Fourier transforms. So representing functions in terms of either known simple functions or points in space is extremely important in physics, and particularly in computational physics. We need to do this in almost all of computational physics. It'll allow us to find solutions for physical problems and to find the properties of the systems we're modeling. So you've encountered this idea already when we were working on differential equations via finite differences. We were representing functions by their values on discrete points in space and time. So there are, of course, lots of different ways to represent a function. I've given a few of those here. So points in space could be thought to be equivalent to using delta functions. Powers of x, polynomials, are extremely common, and simple powers of x are effectively a Taylor series. Trigonometric functions form the basis of Fourier transforms and are very common. In quantum mechanics, you've learnt about using the Legendre polynomials to represent an arbitrary angular momentum. In general, we write a function as this equation shows. So the function f of x is given as a sum over a certain number of these representative functions. We'll call them basis functions. That's a term which is often used in quantum mechanics. So we have a sum over little n of Cn, which is the coefficient, decides on how much of the function will contribute, and then you have the basis function Bn of x. Now, thinking about how we find those coefficients, formally we can use matrices, though often we'll use a fitting or a least squares approach to data that is known. We can optimize as well. That's something that's often done in quantum mechanics and in other areas where you vary the values of the coefficients to maximize or minimize a particular function. Just to look at it formally, if we multiply on the right by a new basis function, Bm of x, then on the left-hand side we can write that integral dx f of x Bm of x as a number, am. And on the right-hand side we can write the integral dx Bn of x Bm of x as a matrix Snm. Notice that we could have written that either way around, so that matrix S will be symmetric. Once we've done that, we can substitute in and we can rewrite the original as a matrix equation. That's the fourth line here. Am is equal to the sum over n of Cn Snm. And then by inverting S, we could find the coefficients Cn as the inverse of that overlap matrix SNM acting on the values AM. Notice that matrix inversion can be extremely time consuming, and as the matrix S becomes large, i.e. it has large numbers of rows and columns, then the time required, this computational cost, will scale as the cube of the matrix size, the cube of the number of rows and columns. Also, you can end up with matrices that are extremely difficult to invert. There's a famous example called the Hilbert matrix that comes up if you're just using simple powers of x to represent the functions. Practically, we'll generally use a pre-written routine. There are routines in SciPy that we'll be talking about, and you won't need to worry directly about how we do this. Using a representation will allow us to solve for the values of an unknown function between the data points. This is a process known as interpolation because it is going between known points. But you have to be a little bit careful. It can be an inherently dangerous process. Extrapolation, where you are using data points to go into a domain where you have no data, is much more dangerous. It is something that you should try and avoid doing. It's always extremely perilous because you don't know how the function would be behaving in that area. Interpolation itself can be dangerous as well. If you look at the diagram, you can see an example of a smooth black line. That's the original function. Then we have some red dots, which represent the data points where we've sampled the function. The rather wiggly blue line is a polynomial that we fitted to those red dots. Notice that it does actually pass through the dots, so technically it's actually fitting the data you've given it, but we've used in this case a polynomial which has a much higher number of terms than we have data points. So I think this was actually a 40th order polynomial. We have 10 data points, so it's undefined, and we therefore get an extremely bad representation of the function. When we're interpolating, we need to think about the domain over which we're actually fitting. Do we want to do local interpolation, where we're using 1, 2, 3, 4 points, or global interpolation, where we're using all of the data points? With local interpolation, one of the classic approaches is called a spline. Cubic splines are frequently used. They're piecewise polynomials, which means that they only fit to one interval between two data points, and then you have a new polynomial between the next set. Cubic splines fit a cubic, as you would imagine, and they produce polynomials which are continuous at the data points up to the second derivative. They're extremely widely used, and there are many useful routines for fitting them. A global fit, where you're covering the whole domain, will use a family of functions, normally either polynomials or trigonometrics, going up to a certain order n. The most common include Legendre polynomials and Chebyshev polynomials. Chebyshev are very easily generated by recursion. In both cases, you typically define them over a specified range, say -1 to 1, so you may have to rescale your data. And a least squares fit will be made to get the coefficients. You do need to be careful with your polynomial order. There are SciPy coefficients for cubic functions for cubic splines and for Chebyshev polynomial fitting, which you will be looking at in the exercises. So I encourage you to go and try the exercises now. This afternoon there will be interactive help on the Moodle Blackboard available for you, and I will post the worked answers to the in-class tutorials as usual on Tuesday.